Good morning, students. Today we are going to learn about Werner's theory of coordination compounds. Swiss chemist Werner was the first one to explain the formation of coordination compounds. In 1823, it put forth this theory called Werner's theory to describe the structure and formation of coordination compounds. And for this theory, he got the Nobel Prize and he is also known as the father of coordination chemistry. Werner prepared a large number of coordination compounds and studied their physical and chemical behavior by simple experimental techniques. He also mixed cobalt 3 chloride with ammonia and prepared around 4 coordination compounds and studied their properties. And based on their properties, he was able to give the postulates for his theory. Werner isolated cobalt complex from the reaction of cobalt chloride and ammonia, and he studied the cobalt complex based on its precipitation reactions with excess of silver nitrate and conductance measurement. When the compound COCl3 6NH3 is treated with excess of silver nitrate, 3 moles of AgCl are obtained from 1 mole of the compound. That is, all the 3 chloride ions are precipitated. On the other hand, when the compound COCl3 5NH3 is treated with excess of silver nitrate, 2 mole of silver chloride are obtained. That is, only 2 Cl minus ions are precipitated. This means that the compound COCl3 6NH3 has 3 ionizable chloride ions, whereas in the compound COCl3 5NH3 only 2 chloride ions are ionizable. Similarly, if you take the compound COCl3 4NH3, it gives only 1 mole of silver chloride when treated with excess of silver nitrate, which indicates that complex has only one ionizable chloride ion. Then Werner did the conductance measurement. The measurement of molar conductance of solutions of coordination compounds helps to estimate the number of ions furnished by the compound in solution. By comparing the molar conductance of the solution with those of some known electrolyte, Werner was able to predict the number of ions present in the solution. For example, it has been observed that the complex COCl3 6NH3 behaved as 1:3 electrolyte, and the next complex COCl3 5NH3 behaved as 1:2 electrolyte, and the third and the fourth complex COCl3 4NH3 behaved as 1:1 electrolyte. Based on all the experimental findings, Werner predicted the ions which are ionizable will be called as primary valency, and they will be present just to satisfy the oxidation state of the central metal. Whereas the ions which are non-ionizable will contribute to the secondary valency, and they are present to satisfy the coordination number of the central metal atom. On the basis of these two experimental findings, Werner said to the central metal atom or ion, there will be two linkages, namely primary linkages and secondary linkages. The primary linkages are ionizable and they will be satisfied by negative ions. For example, If you take the first complex COCl3 6NH3, it has 3 chloride ions as primary valency, because when you are going to treat this complex with X silver nitrate, you get 3 moles of silver chloride, which tells us these 3 chloride ions are present outside the coordination sphere and they are ionizable. And so only this complex is having the conductivity ratio of 1:3 electrolyte. If you take the entire coordination complex, that complex will behave as one electrolyte and the 3 chloride ions will contribute to the conductivity of 3 electrolytes. So only this complex has the conductivity of 1:3 electrolyte. So when he tried to give the formula for this complex, he wrote the central metal atom which is directly attached to 6 ammonia molecules within the coordination sphere, and he wrote the 3 chloride ions which are ionizable outside the coordination sphere. Now let's discuss about postulates of Werner's theory. In coordination compounds, metal atoms exhibit two types of valencies, namely the primary valency and the secondary valency. The second postulate is that the primary valencies will be ionizable, whereas the secondary valency will be non-ionizable. In modern terminology, we can say primary valency corresponds to oxidation state of the central metal atom. For example, in the cobalt complex COCl3 6NH3, the primary valency of metal atom, that is cobalt, will be equal to +3, that is its oxidation state. And this primary valency will be satisfied by negative ions, and here it will be satisfied by 3 chloride ions. The third postulate is that the secondary valencies are non-ionizable and they will be satisfied by neutral molecules or negative ions. In modern terminology, we can say secondary valency will be equal to coordination number of the central metal atom. We know coordination number means number of donor sites that are directly attached to the central metal atom. If you take the complex COCl3 6NH3, the secondary valency of cobalt will be 6, since the cobalt atom is directly bonded to 6 ammonia molecules. And if you take the next complex COCl3 5NH3, the secondary valency of cobalt is also equal to 6, since the cobalt atom is surrounded by 5 ammonia molecules and 1 chloride ion. The fourth postulate of Werner's theory is that there are two spheres of attraction around a central metal atom or ion in a complex. The inner sphere is known as coordination sphere, and the groups present in this coordination sphere will be firmly attached to the metal. The outer sphere will be called as ionization sphere. The groups present in the ionization sphere are loosely bound to the central metal ion, and they can be dissociated into ions when this complex is dissolved in a suitable solvent. If you consider the ions or the neutral molecules bound by the secondary linkages, they are present in the coordination sphere of the central metal. Hence, they will be held firmly by the central metal atom. This gives the definite spatial arrangement corresponding to different coordination numbers. For example, if a metal ion has 6 secondary valencies, they are arranged octahedrally around the central metal ion. If the metal ion has 4 secondary valencies, they are arranged in either tetrahedral or square planar arrangement around the central metal ion. The secondary valency thus determine the stereochemistry of the complex. On the other hand, the primary valency is non-directional. Now let us discuss about the limitations of Werner's theory. The first limitation is that Werner was not able to explain why only certain elements form coordination compounds. The second limitation is that he said if the coordination number of the central metal atom is 6, shape of the complex will be octahedral. If coordination number is going to be 4, then the shape of the coordination polyhedron may be square planar or tetrahedral. But he did not explain why these directional properties are there. And the third limitation is that he did not explain why coordination compounds are colored and why they are having characteristic magnetic and optical properties. Now let's discuss about the frequently asked questions based on Werner's theory. The first question is, when a coordination compound CrCl3 6H2O is mixed with excess of silver nitrate, 2 moles of silver chloride are precipitated. You have to give the structural formula of the complex and its IUPAC name. In order to answer this question, the clue given for you is it precipitates 2 moles of silver chloride, which means 2 Cl minus ions are ionizable. So you will write 2 Cl minus ions outside the coordination sphere. And we know coordination number of chromium is 6, which means it can directly bond only with 6 donor sites. So inside the coordination sphere, you will write the central metal atom chromium and 5 ligands. So you will have 5 H2O molecules and 1 chloride ion also will be inside the square bracket. Then outside the square bracket, you will be writing 2 chloride ions and 1 H2O molecule. And we know to name this compound according to IUPAC nomenclature. The second frequently asked question is, the molar conductivity of the complex COCl3 4NH3 2H2O is found as similar to 3:1 electrolyte. What is the structural formula and IUPAC name of the complex? Here the clue given is this coordination complex will be similar to the nature of 3:1 electrolyte. We know the entire complex ion will be acting as one electrolyte or one ionic species, and this 3 will be contributed by 3 ionizable ions which are outside the square bracket. So the formula of the complex will be CO NH3 4 times H2O2 and 3 Cl minus ions outside the square bracket. Then only this complex will act as 3:1 electrolyte. Students, try to solve this third question on your own. This is the intext question given based on Werner's theory. If you take the first coordination compound palladium Cl2 4NH3, it precipitates 2 moles of AgCl when this compound is treated with excess of silver nitrate, which means it has 2 ionizable Cl minus ions. So now you try to find out what are the molecules or ions which will be present within the square bracket and what are the ions which will be present outside the square bracket. Since it precipitates 2 moles of AgCl, 2 Cl minus ions will be present outside the square bracket. Now try to find out what is left out. So the left out will be inside the coordination sphere and it will be palladium NH3 4 times. So secondary valency, that is the coordination number of the palladium, will be equal to 4 since it has only 4 ammonia molecules which are directly attached to it. Same way, try to solve the other intext questions. Students, kindly check whether you are able to answer these questions.